Imagine this for me. You're waltzing through your local livestock fair, just riddled with typhus and smallpox because it's the year 1906, baby. Some English bloke asks you to guess the weight of his ox. Weird, but you throw out some guesses all willy-nilly, just hoping it was somewhere in the ballpark to feel good about yourself. Little did you know, your random guess and 786 others would make history that night.
One Sir Francis Galting of Birmingham would go home after the fair with all the guesses that he recorded, including yours, to find that some guesses got close, but none got the actual weight of the ox. But wait a second, he said, probably smoking crack. What if I take the average of all these guesses?
When he took the average of every single one of those guesses combined, he got the quantity 1,197 pounds. The actual weight of the ox? 1,198 pounds.
Galton would publish his findings in a paper in 1907 where this phenomenon became known as the wisdom of the crowd. Galton had just changed the future of statistics, psychology, and reasoning itself.
And that was the only good thing he did for society, because right after that, he basically created eugenics. So I think he's gotten enough screen time by now.
In a nutshell, the wisdom of the crowd refers to the idea that the collective decisions made by a group of people will always be more accurate than any one person's or any one expert's decision. You might have seen this phenomenon in this Vsauce video, which is where I got the inspiration to do all of what you're about to see.
Now, this idea is applicable in two different ways. One that deals with the psychological and socially theoretical aspects of it, that deal with ideas like, epistemic humility and the limits of human intuition, or the debate of a true democracy versus a republic or oligarchy of experts or elected leaders. Or there's the mathy quantitative side to it. And since half of my generation can't even read proficiently, I think it's safe to say we can stuff all that Aristotle jargon for today. My goal here is to present the math behind the wisdom of the crowd, how it works, and proving that it works by forcing my socially awkward ass to fly across the country to gather the guesses of the greatest young minds in America at Yale University and putting them up against the guesses of my random ass Chicago suburb to try and find the answer to one of life's most daring and pressing questions that have ever been conceived of. How many M&Ms do you think are in this bag?
Are in this bag.
That's outside. This is the dorm of a random college kid that I kicked out.
But the only way to actually see if my simulation is accurate is by counting every single one of these M&Ms. God help me. I never want to think, see, taste, or even imagine an M&M beyond this point in my life. The results of this study are going to throw you for a loop, I guarantee it. So if you love learning, stick around, learn with me. For now, I think it's time I introduce to you my findings on the math behind the wisdom of the crowd. Now you may be asking to yourself, well, wait, what math is there to show? You just gather up all your guesses, add up all their values, divide by the number of guesses, and boom, you got your average. Just compare that to the true value, right? Well, to that I say you're quite perceptive, my child, but what if there was a way where we can take the individual guess and predict how far off that should be from the actual value, and then take the average and predict how far off that should be from the true value, and then compare the two and see if the wisdom of the crowd is actually correct in that the individual guess should be farther off than the average without even having to know the true value. So, with that in mind, let's dig deep.
To do this, we're going to use 5 fundamental statistics formulas/measurements. Mean, standard deviation, variance, mean absolute deviation, and standard error. But first, before we do all that, let's define our variables. N is going to stand for the number of data points, or guesses in this case. X subscript I is going to represent the guess made by person I. So the first person I survey would be X subscript 1, the second would be X subscript 2, and so on. This guy is pronounced x bar. He's going to represent the value of the mean. S of x is going to represent the value of the standard deviation, and s squared is going to represent the variance. You may have seen standard deviation or variance defined by these variables. However, these variables represent population. We're going to be measuring sample. This is because we're not surveying the entire population of a certain category of people. I'm only interviewing a certain subsect of Yale students, or I'm only interviewing a certain subsect of people in my city. We're going to use the variable SE for standard error. Finally, since I'm a lazy bum who couldn't think of anything more creative, we're just going to use the variable MAD or MAD for our mean absolute deviation. Now let's define our concepts. Mean is the easiest of the three. It's just a fancy way of saying average. We calculate it by taking the sum of all the value of the data points and dividing by the amount of data points there are, which in its most sophisticated form looks like this. Now don't worry, don't lose your shit because you've never seen this E thing before in your life, or you just haven't seen it in years. This is what we call summation notation. It just means the sum of whatever you're measuring. This index tells you which value to start at, which will be 1 in our case, and this value tells you which value to stop at, which will be n in our case, or the last one. Alright, so these next three measurements are all very similar in that they measure the variability within a data set. However, they vary in the ways in which they calculate it. So let's start with standard deviation. Standard deviation tells us how far the average data point, or guess in our case, is from the mean of its data set. Keep in mind that this measures average individual guess or data point. Essentially, the higher the standard deviation, the farther it is away from the mean. It's calculated by taking the squared deviation of every single data point, adding up all of those deviations, and then dividing by the amount of data points you have, and then square rooting that final quantity. Here's what that equation looks like. Hey, it's okay, don't worry, don't be scared, I'll hold your hand through this. Remember, it's our friend, Big E, whose actual name is Sigma. Now, like before, we're adding up the value of a bunch of numbers, but instead, it's the sum of all the quantities we get when we replace x subscript I with its respective number. Meaning, it's the sum of x subscript 1 minus x bar squared, then the sum of x subscript 2 minus x bar squared, all the way up to x subscript n, or the last guess. And remember, x bar is just the mean. So really, all this is just the sum of each individual value minus the mean quantity squared. The rest is really easy. Divide by n minus 1, or the number of guesses minus 1, and then take the square root. Now that wasn't so bad, was it? Next, variance. Variance is calculated by using this formula. Oh wait, my bad. That was the wrong paper. That's the last formula, isn't it? Nope! Just kidding. Get this. Variance is simply the square of standard deviation. That's why the variables for variance and standard deviation are s squared and s respectively. Variance is essentially the ugly stepbrother of standard deviation, since you can't really do anything, you can't really interpret anything from variance alone. You have to calculate it and put it into other formulas in order to get a readable number. Now you may be asking, well, why do we even need variance then? Can't we just use standard deviation? Well, without it, our next equation wouldn't exist, because standard deviation scales much differently than variance. Also, we can't directly add standard deviations. Plus, you get to learn more. Is that not why you clicked on this video? If variance was the ugly stepbrother to standard deviation, mean absolute deviation is the hotter, straight-cut older brother to standard deviation. This is because standard deviation and variance both use squared values in order to determine variability. This makes them more sensitive to outliers in the data. However, MAD, mean absolute deviation, uses absolute values, which means whatever we get from MAD is going to be how far off the average individual guess is from the mean. Here is the MAD equation, and again, it's very similar to standard deviation and variance. However, you see those absolute value signs because it calculates the average absolute difference between each data point and the mean of the data set. This is going to be our equation for standard error, also known as the standard deviation of the mean. It's the same thing. I'm going to call it both depending on what mood I'm in, so you're just going to have to deal with it. Let me explain how we got this equation because it seems too simple to be true. First, we have to note that because each of these guesses are random, independent outcomes, we can directly add them together. If they weren't, we simply couldn't. Why? I don't know, Gavin, do you know why?
I don't know, them's the rules.
Wow, you're so smart. Anyway, this allows us to evaluate this quantity. Because these are all equally random variables, they should share the same variance, so all we need to do is multiply by n in order to get the value, since we're adding the variance n amount of times. So, the variance of all the guesses combined is n times s squared. Keep all this in mind. Now, we're trying to solve for the variance of the mean, or the variance of all the numbers added together and divided by n. Here's another thing I have to note. Because statistics is just weird and wants to be different, when a random variable is multiplied by a constant, the variance is multiplied by the square of that constant. So it'll look like this. It sort of operates in the same fashion as raising the argument of a logarithm to a power, but not really. You may be thinking, well, we're dividing in this equation. Why are you wasting my time with this? But, my friend, dividing by n is the same thing as multiplying by 1 over n, meaning our equation now looks like this. But, remember when we said this quantity equals this in the beginning? So, when we square this value and substitute this value, our equation suddenly becomes much more solvable. Just multiply these out, cancel, and we are left with s squared over n. This is our equation for finding the variance of the mean, and all we have to do when we get these values is square root this quantity to find the standard deviation of the mean, or how far the average of the guesses should be from the true value. Boom! We see that due to this formula, the amount of guesses is inversely proportional to the variance, which occurs because the randomness and polarity of the guesses will eventually cancel each other out. This perfectly simulates how the wisdom of the crowd works, even when we don't have the true value. Almost. See, when we're finding the variance / standard deviation / mean absolute deviation of the individual guesses, we're finding how far away they are from the mean. Whereas when we're finding the standard deviation of the mean, it estimates how far away it is from the true value. There really is no way of calculating how far the average individual guess is from the true value without actually knowing it, at least that I found. But it's already proven that the mean of all the guesses should be close to the actual value, so that's why I think it still has credibility. So TLDR, mean is the average of all the guesses or data points. MAD is going to tell us how far away the average individual guess is from the mean. Standard error is going to tell us how far off the mean is from the true value, and we're going to use standard deviation and variance to calculate for standard error. Alright, you're almost done. Here are the steps we're going to take to simulate the wisdom of the crowd using all these statistical tools. First, we get the mean of the guesses, obviously. Then we calculate for each guess's deviation, so basically the mean minus the guess. Then we plug those deviations into our variance formula to get our variance, and then square root that to get the standard deviation of the individual guesses. For our MAD, we're going to have to just calculate every single guess using the formula. It's not as smooth a transition as variance into standard deviation. Finally, we plug our variance value into the standard error equation, and we get the standard error of the mean. Then we compare the MAD of the individual guesses and the standard error of the mean and see which one's closer. That's it. That's all you need to know. Alright, back to real me.
Wow, that was a whole boatload of learning you just did there. Doesn't that make you feel exhilarated? Like enough to want to fly across the nation to the country's debatably top university just to test it out? Speaking of which, I believe I have a flight to catch.
The plan is simple. Break into Yale's campus, awkwardly ask students who are on summer break who don't want anything to do with me to guess the amount of M&Ms in the bag, and then crunch them numbers. Enjoy this little fun flight montage for now.
So as you can see, I did it. I invaded Yale without them noticing. That's outside. This is the dorm of a random college kid that I kicked out because all I had to do was wear a suit and look important, and you kind of get whatever you want here if you just have a suit. It is so incredibly hot in here. That's why I look like I've been through a tornado and a car crash both at the same time. There's no AC. All I have is a little dinky box fan right there. So that's fun, but it's okay. I was able to sneak our goodies both into Yale and TSA. Can't catch me yet. I just hope the students are a better reflection of the school than the dorms, because, oh my God, it is terrible. But I'm a man of science, and I'll do whatever it takes, even if it means sneaking candy through TSA, kicking out a college kid out of his dorm, ruining his life potentially, and going through this heat. So let's hope it's good. I really hope so, dude.
After so long, my harassment of college kids for my silly little experiment had finally begun, and the guesses started rolling in.
1,000?
1,000? Okay.
250.
250? Yeah, all you have to do is guess the right answer. You should deliberate, try and create, try and find a guess, like you guys using your brains together. I don't even know how many are in there.
Oh, okay.
Yes, that's all. You guys can talk to each other, you just can't. Here you go.
How do we get in? Are we starting? Exactly right?
You'll see.
We just got done with finals.
Finals, there's no like brain cells left to give, unfortunately.
Well, whatever's left, well, the one cog that's left in the brain turning.
3,000?
3,000? Yeah. Okay.
3,000? Well, I have some mind that if you just grab a very small amount of rice and you guess how many pieces,
Oh.
it's always usually
It's usually higher than you think.
much higher than you.
Okay, that's a very interesting perspective. I like that.
I don't know if there's any logic to it.
I don't even know. Like, how would you estimate? It's like not. It's like a, you know, like a bag.
On that. You know,
What if I
like
just
different
went away with
quartiles, you know what I'm saying? Like,
You can do this. You can screenshot. How many chances do we have to guess?
You have as much as you want until you get like one final answer. You get take as
Oh, yeah.
2,500 in this thing? What? There's no way, bro. That's like maybe like
1250.
You guys know the actual
This is exact. No, I
We
know
don't.
the exact number.
You're gonna count it.
726.
1250. That's my final.
No, no.
Yeah, we don't know the answer. Y'all just gotta use your brains together.
Way too low.
634 is too low.
636.
No way there's a 1,000.
636.
bro.
You don't think there's 1,000?
What do you think this way is? How much do you think one M&M weighs?
Like
so should we count this quarter
Yeah, and then
you can do.
We're not gonna
No,
count
we need
them.
to even this.
You guys can do whatever your heart desires.
You didn't cross. Yeah, exactly. Get like, do like an inch by an inch. Yeah, exactly. This quarter, like, yeah.
I've never seen this done before, but you guys are definitely doing something right.
Ten, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
About 12. 3. No. Take 2, 3, 4, 5. In between, look up. So 60.
So that's my area.
Yeah, just do it by area then if you really want to play that game.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Keep counting.
There's about 20 across. There's about 20
16,
across, right?
17, 18,
There's about
19,
10 up and down, and then there's like 5.
Okay, maybe actually you're right.
So like 50 times like 20.
So 9.
Like you're at least at 1,000 low key.
24 by 25. That's
You got that?
approximately
24 times 25?
Yeah.
600. Thank you.
600.
600?
I feel like we should make it like 600. Because there's the there's the Z, X, Y, I think this is flat, so I think there's. Oh wait, add an extra 100.
Yeah, add an extra.
I'm not kidding. I'm not kidding. 700.
705.
a different answer.
Yeah.
Yeah.
In full.
So split it into like quartiles, you know what I mean? Like every, like how close do we think we are with that?
Oh yeah, what's the plus or minus, right?
I think the plus or minus is let's say different.
Each, but there's 5 of us.
I think it's about 300.
300?
Around 920.
920? Okay.
I'll say 375.
I would say 500.
1,200.
1,200? What's your guess?
1,500.
1,500?
Like low-key 1250.
No.
Low-key 1250. I'm
It's-
sticking with my guess.
It's not. It's 960. 1,720.
1,720? Okay.
I was gonna guesstimate like 700.
700.
Answer's like 1350.
So 1350,
Final answer 846.
846,
720.
720,
I'll go with 1250.
1250. How much?
1,400.
1,400.
14. Wow.
All right, so let's make sure we have 650, 675, 700, 715, 777.
Maybe it's just 300.
300? Okay, so we have, yours is 10 times the amount that he has.
300 is way far from the right answer.
Okay, thank you guys so much. All right, so the guesses have officially been all gathered up. I still have to talk quiet because there's still people in my dorm, and I don't want to seem like a weirdo. We have a grand total of 55 guesses. Not bad at all, considering it's summer. The students were all very, very nice. They were all very, very approachable people. So Yale students, thank you. Thank you so much. They're all very, very intellectually curious people. Considering a stranger with M&Ms is asking them to count them all, or at least guess. So thank you. Thank you so much. This was a very fun experience doing this. It's the first time I've ever done anything like this. So thank you, Yale, for allowing me to harass your students. But now all the data has been gathered up. Time to fly home. Do it all over again. Can't wait. Now let's head home. What, you wanted another flight montage? I already got enough dirty looks in the airport from the first one. All right, so it's time to crunch the numbers we got from Yale. I got our friends right here. They look a little sad and musty from the plane ride, but that's okay. After many calculations, and by calculations I mean I did about a third by hand and then put the rest into a calculator, I have all the numbers. I have all the variables that we need. So our mean, meaning all the guesses added up divided by the amount of guesses, from Yale is 935, rounded to whole numbers. We're going to be doing whole numbers because it makes my life easier. And by the way, the median, the number right in the middle when you put the numbers in order from least greatest to greatest, is 777. So God is quite literally on Yale's side. The variance from Yale is 407,125 with a standard deviation of 638. Now remember, you have to take these numbers with a grain of salt because, again, we're working with squared values here. However, there is one more reason I wanted to use standard deviation, and that's for the empirical rule. So get ready to learn more, put your thinking caps back on. The empirical rule states that a certain percentage range of data should fall within a certain amount of standard deviations from the mean, depending on how many standard deviations you take. The 3 percentage ranges are usually 66%, 99%, and then 99.7%, with 68% being within 1 standard deviation, 99% being within 2, and then 99.7% with being within 3. Meaning 68% of our guesses should fall within plus or minus the standard deviation that we get from the mean. Now let's apply that to our Yale data. Remember that our mean is 935 and our standard deviation is 638. That means 68% of our data should fall between 935 plus or minus 638. Meaning 68% of our data should fall between the numbers 297 and 1537. Why did I spend all this time explaining this to you? Well, because a little bit more than 68% fell within that 1 standard deviation's worth of range. 85% of the guesses were within 1 standard deviation from the mean. Now, here's why that number is very interesting. Our standard deviation of 638 is relatively high for what we're measuring. Yet 85% of our guesses were within 1 standard deviation. They were very closely knit together with such a high standard deviation? That's because the outliers were so far apart that they brought the standard deviation up so much. And here's how I know the outliers are really, really far apart. If you were to trim the top 5% of guesses in terms of value and the bottom 5 guesses, our standard deviation drops from 638 to 413. So we have really far outliers, yet 85% of our guesses are within 1 standard deviation, meaning Yale can either be extremely confidently wrong because their guesses agree so much, or they are right on the money, basically. I wonder why they are so close together. Anyway, our MAD equaled 455. This is our number that we'd like, which means the average individual guess was 455 M&Ms away from the mean. Our MAD is especially high in comparison to the standard error, which is 86. This means the mean of all the Yale guesses should be 86 M&Ms away from the true value. Not bad. You guys did amazing. All the guesses are right here, so if you want to check my math or make me feel stupid, feel free. 86 is the number to beat, so hopefully my suburb can get at least remotely close to that. Anyway, all of our learning has finally come to fruition. Time to do it all again. All right, so we're here. I don't know what to say.
So It's just so hard to get into one spot.
All right, so we're finally here, back in Chicago. There's a lot of people, and I'm kind of scared. Hopefully, they're not mean to me. Oh, hey, it's me again. Yeah, this guy had no clue what he was in store for. So obviously, some time has passed. You can tell because I finally got a haircut. I have no footage. I have no footage of the guesses from Chicago. So we went to a public park where a concert outdoorsy thingy was taking place because we couldn't think of where else a large concentration of people would be. And they didn't let us record. And by them, I don't mean the park administrators, I mean the people. People are already skittish and reluctant to participate in the first place. I don't know why, it's just a bag of M&Ms. But I just assumed from that demeanor that if I asked them to film, they would just say no. And then if I went to the next people, they would ask, are you gonna film us? And then they would say no. And then it would just cause a whole chain reaction until the entire park knew of a M&M maniac running around. The only footage of people I actually have guessing were these nice people on their porch while we were walking to the park. So here's that.
I'm doing mental math right now.
I know, but you can't say it out loud.
You can tell me, just like...
Not them?
Yeah.
Okay. I'm gonna go with...
1,200. Okay. 245. Okay.
I'm gonna go with 1,000.
Okay.
643.
We don't know how many are in there. Not everybody was super mean and reluctant, including this one guy who gave me his business card and explained that he worked as the property manager for a mall in Chicago. And he told me to email him the correct amount of M&Ms once this whole thing was over. And then I realized why he was so nice. So I did email him on a burner account because you never know these days. And he never responded. So safe to say I won't be working at a mall anytime soon. Also, one guy guessed four M&Ms. And it's like, don't waste my fucking time, dude. So yeah, surprisingly, random Chicago residents are not as intellectually curious as Yale students. As far as the actual numbers for Chicago's guesses, you're just gonna have to trust me, man. It was out of my power. But I will gain your trust by filming myself count every single one of these M&Ms. So if that's not good enough for you, then what are you doing here? I have all the numbers crunched right here. I'm just gonna give you the two variables that you wanna hear because I know your attention spans can't hold me for that much longer. Remember, Yale had a mean of 935 with a MAD of 455 and a standard error of 86. So 86 M&Ms away from the actual value is the number to beat for Chicago. So finally, after weeks, hell, even months of deliberating, planning, and harassing random strangers, the Chicago standard error is 136. Yale wins. I don't know what you expected. The Chicago mean was 1,196 M&Ms, the standard error was 136, and the MAD was 725 M&Ms. So
Whoop-de-doo, when you go to the brightest place in America, you get the brightest guesses. I don't know what to say. But the only way to actually see if my simulation is accurate is by counting every single one of these M&Ms. God help me. If nothing of what I have done so far is worth a like and subscribe, this has to be worth one, right? Link is in the description to the full unedited 1 hour and 7 minutes of me counting these M&Ms. If you really want to just kill your brain. Wow, that took a really long time. I've probably spent more time with these M&Ms than I have with my immediate family. So now it's time to see if my calculations are accurate or if I'm just a dumb, stupid idiot who has no idea what he's talking about. So for the second cliffhanger in this video, the actual amount of M&Ms in this bag is 1,474 M&Ms. I never want to think, see, taste, or even imagine an M&M beyond this point in my life. So the final calculation we'll have to do is subtract the mean of both sets from the true value, and then subtracting the standard error of both sets from those values to tell us how far off the standard error was from being correct. In other words, how many M&Ms off was the standard error from actually telling us the exact amount of M&Ms the mean was off from the true value. The amount of M&Ms that both of the standard errors were off by are on screen right now. Wait, what the fuck? How in the world could Yale's standard error be off by 453 M&Ms when it was only projected to be 86? I mean, what could have happened? I might have miscalculated this one thing, but I quadruple checked everything. I could have, what went wrong? Nothing. Everything went perfectly as planned. Why do you think I called this an experiment or a study and not just a breakdown video or a fun little thing? Why do you think I went to such extreme lengths to get people on the opposite sides of the spectrum of life just to have them do the same thing? That's because I didn't. Watch this. You should deliberate, try and find a guess, like you guys using your brains together. Brains together. And this. You can tell me just like...
Nothing.
Yeah.
Okay. Nothing.
I made it imperative to find Yale students in groups of 2 or more and encourage them to pool their minds together to try and find an answer. Whereas in Chicago, I had them isolate their guesses or found people specifically by themselves. All to prove one thing. The wisdom of the crowd crumbles under bias and influence. So yes, I rigged this whole thing. I knew from the very start Yale was going to lose this battle. Now, before I go into explaining bias, you may be thinking to yourself, well, Chicago was decently far off too, wasn't it? The standard error was 136 and it was off by 142 M&Ms. That's a lot, right? To that I say, yes, you're right. But I will say this. The environment that we were in, a public park during a public concert, it's very hard to isolate guesses and not let bias seep in. People would shout out answers before we even explained to them what to do. People were sitting so close next to each other that different groups would hear each other's answers and then they would already have an opinion formed before they even saw the M&M bag. And it didn't help that most of the people there were already slightly intoxicated. Even with all that in mind, Chicago, with their guesses isolated as much as me and my friends could, were much closer than Yale was. And Chicago was just a bunch of people chugging brewskis in a park. These are Yale students, dude. But how come this bias even threw off the smartest of people's guesses in the first place? Well, I'm gonna tell you, but I'm not gonna tell you based off of research or studies. I'm gonna tell you how I saw it. You see, what I saw was a bunch of students that were challenged by something that they have never even given thought to about in their life. So naturally, when they have no experience behind a challenge, they look to other people to try and help them. I mean, who wouldn't, you know? But when you look at this bag, you already have a predetermined judgment of how many M&Ms you think are in here. But because you believe you have no experience, you start to second guess yourself. And that's when you look to the other people to help factor in their guesses in your own. And that is what ultimately throws off the wisdom of the crowd. Now, with the amount of time and effort I've invested into this video, I've had plenty of time to reflect on the true nature of what I'm doing behind this experiment. And mathematically, yes, influence and bias is what throws off the wisdom of the crowd. But beyond this, in our everyday lives, I do think it has a lot deeper meaning. Now, I know I said I wasn't going to talk about the whole social theory aspect of the wisdom of the crowd, but the truth is, The math aspect crumbles if you don't understand this side of things. Humans are inherently social creatures. This is a known fact. You and I can't exist without others around us. Yet I stand firm in the belief that we are also inherently selfish, valuing our thoughts, our opinions, and our ideas over everybody else's. We are just instilled with the notion that everybody has an equal say or an equal opinion. Now, this is obviously morally correct. Everybody should have an equal opinion. We fought for hundreds of years trying to get past that. But why do you think the world started as a bunch of tyrannies and dynasties and kingdoms and whatnot, and then eventually evolving into republics and democracies where everybody had that equal opinion and equal say? Think about the people that even rose up against these tyrannies. Were they fighting so that everybody can have a voice? Or were they fighting for their voice, convinced that their perspective was the only one that mattered? Now, obviously, all of that is up to interpretation, but it still leaves us with this question. Why did we move to forms of government with democracies and republics, or instilling people with this notion of everybody has a voice in the first place? We know from this phenomenon that it's influence. The influence that people have on each other is what ultimately throws off the trajectory of a decision that may have been the correct one. So is our instinct to hold our values and our thoughts and our decisions in superiority of others given to us for a reason? Well, here's the thing. Unlike that selfish instinct, we aren't born with a certain set of values or ideas or methods of decision making. It's the sum of all the ideas of those around us, the environment in which we are raised in, and the experiences that we go through. This is to say, from the very conception of our being, we are, in fact, influenced. And those that influence us were influenced to believe the things that they do, and the same before them, and so on. Now, here's the difference between that kind of influence and the influence we saw in the experiment. All those students saw that bag and had an answer in mind. Those that changed from their original answer that would have ultimately led to their crowd being correct, changed it simply because somebody told them to. And that's the thing. The influence that we witnessed in the experiment wasn't real influence. It was shallow, it was reactive, it was baseless, it had no experience, no foundation behind it. But real influence is different. It's slow. It builds up over time through our upbringing, our experiences, the ideas that we're exposed to, and the people we trust. The people that fought all those years ago against lack of representation were influenced by years, decades, even centuries of subjugation. You see, that influence is what makes the wisdom of the crowd work. Because when each person brings their own lived perspective shaped by a diverse web of real human influence, the collective average is not just a number. It's the best estimate that humanity has. The wisdom of the crowd works not in spite of influence, but because of it. And according to Michael of Vsauce, it's what led us to evolve to leave the authority of thinking, not to a few great minds, but to the great mind. Thank you for watching.